for this year's talk series in Winds and Outflows. And today we're going to hear talks on two different types of this phenomena, on stellar winds and outflows from tidal disruption events. Both speakers today are local experts that we're very lucky to have among us. So first we'll hear from Andrea Dupree on stellar winds, and then we'll hear from Kate Alexander on tidal disruption events. And just a quick note on the format, so like in the previous 2 weeks, after the second talk, we will take a short break so that everybody can get pizza, and then we will reconvene and have a short discussion with both our speakers.
Okay. Thank you. Thank you for inviting me, and thank you for coming. I see some familiar faces who are interested in winds, and that's terrific. Okay, let me go through this. I probably have too much information, so let me just start and go through quickly, we hope. Is this going to work? It's not going to work. Why isn't this going to work? This is supposed to work, and it doesn't. What's happening? Why isn't this going?
Can you do the
there? Yeah, but well, no, that's what it didn't do. There, now it's now it's going. All right.
Okay.
Don't ask. Don't ask. Okay. Why do we care about stellar winds and mass loss? Lots of reasons. 2 weeks ago, you heard Aaron Daughter speak about the effects of different mass loss laws or relations on stellar evolution and color magnitude diagrams. Stars with their winds can enrich everything around them, the interstellar medium, the intergalactic medium. The type of mass loss, the phasing of it, whether it's constant or bursty, will affect, for a supergiant star, will affect the type, the flavor of supernova that develops. We're interested in stellar mass loss because of angular momentum evolution. How do stars spin down? And from many of the cool stars, we're able to estimate ages using the spin down formulae. Lately, of course, these stellar winds can erode the atmospheres of exoplanets, a topic of interest to many of you, as well as produce chemical abundances and change the environment around these various stars. Let me just remind you what happened back in the old days when you could just look at a star and get a spectrum, and how did they know there was a wind from the star? And this happened actually back in the 30s when two astronomers, Adams and McCormick, saw circumstellar lines that were always blue shifted in the spectrum of an M supergiant. And they said, maybe the atmosphere is expanding because they're narrow lines, they're from a circumstellar shell, and they're expanding. Spitzer, however, it was interesting, wrote a paper, said, no, that's not going to happen. It's just a circulation pattern. So what you see expanding is really going to fall back down again, and it's not going to be a wind. One could say perhaps that the most firm detection was an observation of a binary star, Alpha Her, where using the companion to the bright M supergiant, they could detect circumstellar emission, which had come from the M supergiant at the escape velocity. And this is going to be a theme that runs along many of these detections, and that is, are you just observing a flow, an outflow that might then be an inflow, or are you observing something that will actually get away from the star and escape, a true wind? So let's start at home. Let's start with the sun. And this is sort of an interesting story because they didn't look at the sun to infer that there was something coming from the sun like a wind, but they looked at comets. And as you know, a comet has both an ion tail, this blue thing, and a dust tail. And what astronomers and I guess people in general noticed that the ion tail, as the comet goes around the sun, the ion tail always pointed away from the sun, but the dust tail followed the orbit of wherever the comet had come from and was going. And back in 1951, Biermann said, there must be something coming from the sun. There must be some sort of corpuscular radiation that the sun is giving off. And of course, it was Gene Parker who suggested that indeed the sun had a thermally expanding atmosphere in his famous theory of the solar wind. But it took the Mariner spacecraft to actually go out and measure and catch a piece of the solar wind and say, we have it. It really is there, and all the theorists were right. Even more, the satellite Ulysses did something amazing. It actually circled the sun. Here's a sun, an image of a sun in X-rays, and you see the dark areas, which are coronal holes, and we know there's a low-density corona there, and that's where the magnetic field from the sun is generally radial, making it very easy for material to escape. And the Ulysses satellite actually flew around and over the poles, and on the right you see the results of what they found. This shiny white, or this white line, I guess white and red zigzag line, indicates the velocity that they measured as they circled the sun. And you can see as they went over the poles here, the North Pole, South Pole, that the velocity is very high, sort of 600, 700 kilometers a second, and near the equator, the velocity is very low. So this was wonderful confirmation that where the magnetic fields are open, you have a very fast but a low density, low mass carrying wind, and where the magnetic fields are generally closed, but clearly there have to be some open field lines here to let the more massive wind emerge. And when we look at the sun as a star, we do see that there is a cyclical variation in the mass loss from the star, from the sun. If we look at the coronal hole area shown in the top, you see when the area is low, the mass flux rate is high, meaning which just reinforces the fact that from the open corona, the coronal holes, it's maybe a fast wind, but it doesn't carry very much material. And you can see the other very obvious characteristic that we will see in all the stars is that the speed varies with the solar cycle. So there's variation in the speed and also in this is the mass loss rate. By this is a factor of 1.5 or 2. So that's when we look at the sun sort of as a star. Now I'm going to take you on a quick trip through all kinds of stars, hot, young, old, cool, luminous, big, small, and we'll see what we can find out and how we detect these winds. The first one to start with are the hot stars. These are sort of O and B stars, very luminous, where they have an expanding atmosphere. And maybe you all know the story of the P Cygni profile, where if we're looking at the star from the bottom, this hemisphere is expanding out, this hemisphere is expanding in the other direction, but all this whole extended atmosphere produces an emission line and also a blue shifted absorption line, and when the two are added together, you get the typical P Cygni profile. And it was Don Morton, I believe, who flew the first rocket experiment. He was at Princeton, flew the first rocket experiment to get a spectrum of a hot star. And lo and behold, this is from a paper by Snow and Morton. God, that's awful. Sorry about that. A paper from using data from the Copernicus satellite, and you see these enormous P Cygni lines like this. This is carbon-3, this is H-alpha, Lyman alpha, excuse me, and this is nitrogen-5. So you see big, strong P Cygni absorption. You see very fast winds. We're talking about thousands of kilometers a second, clearly the escape velocity. And there was no hint of this from any optical spectra before, because optical spectra probe the lower atmosphere where the velocities, if they are measured, are very low. 5, 10, 20 kilometers per second. But here we're up into the thousands. So clearly this is a obvious demonstration of massive, fast winds from these hot stars. Now, when we move to cool stars, this gets a little trickier, because cool stars frequently have chromospheres and coronae, i.e. the photospheric temperature drops off, and then it rises again as you go further from the star, producing a so-called chromosphere or corona, probably heated by magnetic waves. So what you have to think about is picking the correct diagnostic. So if we show a temperature profile, this is with height, the photosphere is down here somewhere, temperature drops to a minimum, then the temperature rises as you go away from the star. And different ions are produced at different temperatures. So in other words, if you want to probe the very outer part of the atmosphere, you might look for an oxygen 6 line, further in carbon 3. Those, of course, are in the ultraviolet, which means that you're not going to be doing very much monitoring or things in order to detect those lines, because they have to be observed from space. But then as we come down lower, we find a helium line in the infrared, which is probes around 10, 20,000 degrees, calcium K, the H alpha core. So you need to find the right diagnostic to be able to detect the wind effectively. You can also look at wind material, which is sort of historical wind characteristics, by looking at circumstellar lines or submillimeter infrared emission. But if we want to look at the star itself, we need to find the right diagnostic and then proceed. So let's start with the T Tauri star. This is one of our favorites. It's one of the closest. It's still accreting from a disk, and what's happening is the accreting material is coming in from the surrounding disk, guided by magnetic field lines, and it creates a shock, a hot spot on the surface of the star. It heats up the corona, and we believe it also drives the wind, a very fast wind. And when we make spectroscopic measurements, whether it's helium at the 10830 helium line or the ultraviolet carbon-3 line, you see not only do we see a P Cygni profile in the helium line, we also see absorption on the blue side of the profile, a signature of absorption by the expanding wind in both carbon-3 and oxygen-6. And the terminal velocity increases with temperature. So we see not only a hot inflow, a hot outflow. Oxygen-6 is formed at a temperature of 300,000 degrees or so, but we also see an accelerating hot outflow. And the outflow, the wind is quite variable. You can see these sequence of 3 nights in H alpha, and you can see it from TW high, and you can see how it's roughly symmetric the first night, and then the second and the third night we start seeing the wind come in. You can also see it develop both in changing in opacity and in extent, velocity extent, by looking at the helium 10830 line. Now, what about other dwarf stars? This, of course, is a pre-main sequence star. It's still accreting. What about other cool dwarf stars like the Sun? Well, this is very tough. There is really no direct measure yet of any wind or outflow from a cool dwarf star like the Sun, or any dwarf star, FGKM dwarf star. However, Brian Wood has tried to infer the presence of a wind by looking at what he calls the astrosphere, or the heliopause. In our solar system, the sun and the solar wind expands, and then when it meets the interstellar medium, it forms a compression, a shock, it gets hot. It's called the heliopause, and this creates absorption in a line profile. So Brian contends that if he looks at other stars, he will not only be able to detect the absorption from our own heliopause, but also from the heliopause around the other star. And that evidences itself in this is alignment alpha interstellar absorption line, and he looks very carefully at the wings of the line and says, well, this is from our heliopause in our solar system, and the left side is from the astropause, which is the heliopause on another dwarf star. And he derives some mass loss rates. I should point out this is very model dependent. You have to understand what the line is like intrinsically. You have to understand the configuration of the wind. You have to understand the configuration of our heliosphere. Suffice it to say there's a number there, but I think that's someplace where we can do some more work. Okay, let's look at some field giants and let's go to more luminous stars. And here's where we've been using far ultraviolet capabilities with FUSE or Hubble or STIS or IUE or something. And you see that all of these stars, now the one on the left is a supergiant, and we see the signature of, well, there's an asymmetry on the blue side of the line, the negative side of the line. Again, a big P Cygni profiles in the ultraviolet lines of magnesium and carbon-3. Another giant also shows enhanced absorption in high temperature, oxygen-6 as opposed to carbon-4. And again, we see the signature of wind absorption in the emission of these particular lines. So there are winds. Every star that we look at that's luminous, we see winds. And the question is, can we look at them in clever ways or better ways and learn more. And one of the most rewarding ones has been this diagnostic from the helium 10A30 line at 1 micron. It's a nifty little atom because this 10A30 line comes from a metastable level. In other words, the helium ion is ionized by EUV photons. It cascades back down into this triplet level. So it builds up a population. So essentially, it sits in the atmosphere forever. And it goes with the flow and maps the wind. And so that's what we're seeing, and we can measure it very frequently because this is done from ground-based telescopes. And you can see here are 3 giant and supergiant stars, and you can see the helium line in some of them is enormous. Beta Dra has a large X-ray flux. We're seeing this great helium line, and we see it in a lot of other stars too, even in P Cygni profile. And these are variable. So we see changes on the order of days. Again, this is in a supergiant. It's here, and 2 days later, it gets stronger, and then it gets even stronger and more extended. And we know that when it goes from the rest wavelength of the line over to this silicon-1 line, we're seeing about 100 kilometers per second outflow. So it's not as fast as the more massive stars, but it's easy to measure, and we can see that. Now, let me move quickly to some globular clusters. These are obviously groups of stars. By looking at them, we can compare a whole sort of family of stars and stellar evolution. The line profiles, again, we see different line profiles. These are optical line profiles, and we see a lot of variability in the wings. Remember that the H-alpha line is formed all through an atmosphere. So the core is formed at the very top where the opacity is highest, and the wings are formed further down in the atmosphere. So when we see these wings and these asymmetries changing, what's happening is the atmosphere is pulsating up and down, but the core of the line is always moving out. It's like a piston that's always just driving the wind out at a constant velocity. And there we find that the calcium line has a higher outflow velocity than does the H-alpha. So again, we're seeing signs of an accelerating wind in these cluster red giants. And we can model these profiles very carefully, and when we do, we can compare it to some of the laws that have been proposed for mass loss rates. And by modeling these profiles, we find values of the mass loss rate that are much less by factors of 10 on the red giant branch than is generally assumed by many of the standard assumptions. And you can ask me about the Reimers assumption. 5 more minutes, okay. The Reimers assumption later. Okay, we look at helium again, and we see the helium line and very fast outflows in all sorts of metal poor stars, whether they're on the HEB or their red horizontal branch or the red giant branch. We find it's a very good wind diagnostic, and we find it in practically every star we look at. The velocities are very fast. That extend by looking at the short wavelength extent of the line. One can see velocities from 50 to about 150, 200 kilometers per second, which it corresponds not only to the escape velocity of the star, but the escape velocity from the cluster itself. And there's been an issue and concern about where the lost cluster material is. Well, we think a lot of it could easily escape, as we find from this. Okay, we can estimate the mass loss rate. Let me skip over that. We can talk about the fate of wind material. We can talk about that later. But then I just have to point out I've left out a lot of things. You can find out characteristics of wind by using eclipsing binaries, where you have a hot star as a probe, and when it goes around behind the supergiant star, you can see the effects of the atmosphere of the supergiant star and get the characteristics of the wind and the wind flow. You could also use submillimeter techniques to measure maser emission, as the middle figure shows here, in an LMC star, and then from that derive both the outflow velocity as well as the mass loss rate. Now, lately, things have really changed and gotten pretty exciting because we've been able to identify the source of these outflows on the surface of stars. Cool stars have spots, and here's a active RS-CDN binary, and we see the modulation of the total light. And when there are spots, it's dim. And when there are spots, we find enhancement of the various lines, including the calcium line. And when there are no spots, we see that the intensity of the line gets weaker. And then it also correlates with the outflow. So when there are no spots, we're able to detect an outflow through an asymmetry in these ultraviolet lines. And when there are spots, the line appears more symmetric. Even more exciting was some things that we had done with Betelgeuse, where we used the Hubble Space Telescope to actually go across the large appearance in the ultraviolet using the STIS, I believe it was. We scanned across the surface of Betelgeuse. Betelgeuse is the largest apparent size of any star in our sky, so it's a nice target. And we found asymmetric profiles that changed not only with time, but as we moved across the star. And when one maps this out, we find sort of asymmetric flows on the surface of the star, in the chromosphere of the star. In other words, in January, everything was moving in. 3 months later, still moving in, perhaps a little bit slower, and then we start seeing an outflow 5 months later. You can see the blue arrows here, and that outflow extends across the surface of the star, another month later. So we're finding these spatially resolved motions and flows and on the surfaces of star. Zeta Puppis there's a really interesting paper out where these folks use the bright constellation of satellites. These are little nanosatellites to do precision photometry on Zeta Puppis, which is an O star, that's a hot star. And they contend that they find changes in the light curve from which they can infer the position of bright spots, not dark spots, bright spots like Betelgeuse on the surface of the star and on a Mercator projection here. And then when they look at the profiles of a line formed in the wind, in particular the helium 4686 line, you can see these patterns, these zigzag patterns, which they then model, assuming that the source of the density enhancement is these bright spots, these bright convective spots. And so they contend that they're finding co-interacting rotation regions, which is what we see also in the solar wind. And we see the same thing if we look at the 4686 line. You see these flows, and you see features that seem to flow out. So we're discovering that there are features on the surfaces of these stars, and we're beginning to understand the source of the winds and the character of the winds. So there are all kinds of winds. This is perhaps a pretty picture that Steve Cranmer produced, showing the whole HR diagram, color magnitude diagram, and the various flavors, the massive stars with the radiative-driven winds, the cool luminous stars where we have pulsation, we have dust, we have chromospheric-driven winds, and then the solar-type stars with the coronal winds. So I think I'll leave it there. Thank you. Do you want a question now or no?
Yeah, so there's time for a couple of questions as we switch laptops. Maybe keep it.
So you had a figure where you had spots and no spots, and then the no spots you had an outflow, and then where it had spots you said, well, the line is more symmetric, but it looked to me like it was asymmetric the other way. Like, was there an inflow, or did it just look that way?
Yeah, I don't know. Maybe it just looked that way. I mean, the real point that we were making, now why don't you take it, is that we did see the asymmetry indicating an outflow in the chromosphere. This, of course, was done ages ago, and I don't think anyone else has done it as looked since.
But it wasn't like the spot was the accretion.
No. That particular one, spot, no spot, was a RS cam band star. It's a binary system that's subgiants, and they're very magnetically active.
Okay, there's no accretion.
Yeah, no accretion. TW high is the only accretion. You have a question?
I was just wondering if these astrosphere models have been tested at all by observations of the helium-1 line. Brinewood's astrosphere.
Oh, the astro. That's a good question. Actually, I have some data which is not reduced. Really trying to do it. Sorry about that. Yeah, that would be a way of doing it. But I'm really skeptical of those models because there's so much that goes into them. They have to assume an intrinsic stellar profile. We don't know what we have a hard time predicting those. Okay, you have to assume what the wind is like, the configuration of the wind from the other star. You have to then figure out what it's doing relative to the interstellar medium, what's going to happen. And then you have to do the same thing for us, because you see the absorption, you also see the heliospheric absorption from us. So.
But there's a lot of data about the heliosphere.
Well, okay, yeah, that's true, and they do look at that, but the part that they're using to get the mass loss rate is the blue side of the line, and that's where it's very model dependent. Yeah.
One of the things that I think we're realizing more and more is that in mass transfer systems, a lot of the action happens through winds, which may precede or a Roche-Lobe filling episode, or there may not even be a Roche-Lobe filling episode.
Right.
So that, of course, complicates things, because now you have the strong gravitational interaction, potentially, with another star.
Right.
So it's complicated enough without that.
Yeah.
I understand. But is there work that's going on now that you think would give some insight into the rate and variability of mass infall to a compact companion, where you have a star that is not a compact?
Okay. Well, we can tell you what the star itself is doing, but then I'll let you figure out what it does when it meets its friend. Actually, this is a very interesting point. There's a huge problem right now about these multiple populations in globular clusters. We don't know what's causing it. And one of the thoughts has been that the evolved massive stars spew out their wind, and then it envelops the smaller stars, and sort of creating a fraudulent star with an enhanced metallicity and things on the outside of a dwarf star. And if you look at the speeds that we're getting, our giants can smother these dwarf stars. So maybe, I don't know. I mean, it might happen. I don't know. Okay, I'm sorry. Let me get out of here.
Wonderful.
Okay.
We just need to switch your microphone.
Oh, yes. Here you go. Did you plug yourself in?
Oh yeah, I'm also.
You're welcome. Okay.
So.
Okay, so now we'll hear from Kate Alexander, and there'll be time for discussion with both speakers after this. So we can continue the conversation further.
All right. Is that microphone in a reasonable position, or? Cool. So I'm Kate Alexander. I'm a finishing graduate student here with Ido Berger, and we're going to now talk about something completely different, which is outflows and accretion onto supermassive black holes by the tidal disruption of a star that passes too close to the black hole. So I guess stars are still involved, but we're interested in the black hole accretion. So just to make sure we're all on the same page, Erin Cara, when she was here last week, actually gave a very nice introduction into tidal disruption events and how you can probe any outflows they generate with X-ray observations. But today we're going to talk about radio observations. So it's, when I say a tidal disruption event or a TDE, what I'm talking about is a star coming in on an orbit that brings it very close to the supermassive black hole at the center of a galaxy, so close that the star passes within the tidal radius. So the tidal forces from the black hole overcome the star's self-gravity. Part of the material gets unbound and is thrown out, and part of the material ends up being bound to the supermassive black hole and will eventually fall onto it, form some kind of accretion disk, and ultimately heat up and accrete onto the black hole. So we can see this observationally, and the first predicted signature of this event is just that the gas gets very hot as it heats up, so you would expect thermal emission peaking in the extreme UV or the soft X-ray. And this was first predicted in the late 70s, early 80s, and then people started seeing events in the soft X-ray with ROSAT in the 90s, and lately people have started seeing events in the UV and optical that are all consistent with this thermal emission. But this is a talk series about outflows, and in fact we've seen that in some cases when a star is tidally disrupted, it seems that a relativistic jet or some kind of other wind is also produced as the accretion is happening. This is not terribly surprising, because if you look at how the predicted mass fallback rate from the material from the star should accrete onto the black hole, if you do a simple analytic calculation, you get that the fallback rate should decrease with time as t to the minus 5/3. If you do some more complicated numerical simulations, you might get something slightly different from this depending on what your assumptions are. But in general, you predict that your fallback rate should peak at a highly super Eddington rate and then decrease with time as a power law. So when we have super Eddington fallback, we might expect super Eddington accretion onto the black hole. And so when you have super Eddington accretion, generally we see strong outflows that are produced. Then as your fallback rate drops below the Eddington rate, you might see the formation of a thin accretion disk. Your outflow might be expected to turn off. And then at very late times, we might get into this radiatively inefficient flows, which is what we see in many AGN that are accreting at this very low rate where there's a hot, puffy disk and a jet that's produced. So assuming there's not some viscous delay in the disk that makes the mass fallback rate not equal to the accretion rate, we would expect to, we think, see evidence of outflows when many of these stars are tidally disrupted. So there are still many open questions in this field. It's a fairly young field. So the most important basic question is, do all TDEs in fact produce outflows, as this basic analytic picture might suggest? What kind of outflows are produced? Are they these relativistic jets, or do you get more of a slow wind kind of a picture? In events where we do see relativistic jets, this actually gives us an insight into how relativistic jets form. When we look at AGN, we're basically seeing the jet in an essentially static state, but here we get to see a jet turn on and off because this is a very transient period of higher accretion. So if we have a large enough sample, we can start to probe why some events produce jets and some do not. Another interesting thing we can probe is, what do the environments around supermassive black holes that were recently quiescent actually look like? If you have an outflow, it's going to slam into the circumnuclear medium around the black hole, and that generates a shock front. And so by studying the synchrotron emission from the shock, you can actually start to probe what the density profile around the black hole looks like. And this is kind of on subparsec scales, so if these black holes are in other galaxies, it would be hard or impossible to resolve any other way. And then, of course, we're just interested in how TDEs fit into the broader picture of accretion onto supermassive black holes in general. People have suggested maybe TDEs actually played a very important role in growing black holes, supermassive black holes to their current sizes. I think that's still an open question, but certainly this is they're an interesting way of probing various accretion processes on more human timescales. So if we are looking for evidence of outflows from TDEs, it's hard to look in, say, the optical or the UV because there's this thermal emission that's dominating. Sometimes you can look for emission lines, but there's also other processes producing emission lines in TDEs, and so it gets a little bit more complicated. As Aaron Kara showed last week, there is some evidence for outflows from X-ray observations. But the simplest way to look for outflows, in my opinion, is just to look for the synchrotron emission that gets produced between the outflowing material and the surrounding ambient medium in the shock front. So you get a very broad power spectrum that's a series of broken power laws. And the peak of this continuum emission, by the time we're typically making our observations, is in the radio band. So if you typically, at very low frequencies, the synchrotron emission will be self-absorbed, and that's a direct probe of the density of the medium. So if you see this self-absorption frequency, then you can directly infer the density, and you can also infer what the energetics of the outflow are, and so forth. So to do this, what we need is a set of radio observations at different frequencies at a bunch of different snapshots in time. So this is our most comprehensive radio data set of any tidal disruption event. This was an event called Swift J1644, which was discovered in 2011. I'll talk about it more later. But we had observations from the centimeter band all the way up through the millimeter, starting just a few days after the event and going all the way out to almost 2,000 days. It's still visible. But what we do is we fit each one of these epochs independently with this broken power law spectrum. So we're not making any dynamical assumptions about how the outflow is evolving with time. And then we assume that there's an equipartition in the energy between the energy in the electrons and the energy in the magnetic fields, which is pretty similar to saying the energy of the system is minimized. It's a reasonable starting assumption. And then from there, you can infer how you get an estimate of the size of the emitting region and the energy in the emitting region. And so you can use this to determine how fast the outflow is expanding, what the overall energetics of the outflow look like. You can infer what the strength of the magnetic field is by this equipartition assumption, and you can infer what the density looks like at each of these times and build up a density profile around the supermassive black hole as the outflow continues to expand. So this is all very interesting and a completely independent probe from what you get from observing the optical and the X-ray emission. So this is the current radio sample of tidal disruption events. As you can see, there are only a few events which are well studied. This is the event I just showed. You can see it definitely has the most comprehensive light curve. But even from this plot, which doesn't have very many events with detections on it, we can already start to see some interesting things. So one thing is there's these group of sources that have very, very bright radio emission over a long period of time. And if you do the full modeling, you find that these events are consistent with a relativistic jet viewed on axis down the jet axis. But you can see from these upper limits that, and these much lower luminosity detections down here, that most TDEs, the bulk of the TDE population, do not produce these relativistic jets. This is not purely a viewing angle effect, because at late times, once the jet has decelerated, the emission should look relatively the same no matter what the initial angle of the jet was. So we're already seeing that there's kind of two types of TDEs. There's some that produce relativistic jets and some that don't. I'm also going to talk a bit about Assassin 14 Li, which has this lower luminosity radio emission. And in this case, we find that the emission is consistent with a slower wind. By slow here, I mean 10% the speed of light or so. So fast by the standards of most other people in the room. Slow only compared to the relativistic jet case. So many of these upper limits could be hiding an outflow like this. So the rate of non-relativistic outflows is still highly uncertain. In the last year or so, we've actually gotten some very deep upper limits on one or two events that are several orders of magnitude below the radioluminosity of 14 Li. So perhaps some TDEs don't produce any kind of outflow at all. And we're trying to figure out maybe those are partial disruptions or they were very viscously delayed and the accretion rate never reached Eddington. We're still trying to figure that out, and continuing to get radio observations of a larger sample will be the best way to continue to probe that. So I'm going to spend the rest of my talk going into a little bit more detail about the two events for which we do have the most detailed sets of radio observations so far, to hopefully convince you that this is all very interesting and we should continue to do this for many more events in the future. So the first one is this event that I've already showed you all of our beautiful full radio data set for. This was an event that was discovered by the Swift telescope. It's unusual for TDEs in that it actually had hard X-ray emission and gamma ray emission. Most TDEs just have very soft thermal X-ray spectra. But the initial X-ray localization from Swift is this big circle. And another thing radio observations can do, especially if it's bright enough you can do very long baseline interferometry, is you can really localize very precisely where the emission is coming from. So the small circle here is the localization of the radio emission, which really showed that this emission was consistent with the center of this galaxy at a redshift of 0.35. So this really helped confirm that this was associated with the nucleus of the galaxy and the supermassive black hole in some way. So if you do all the synchrotron modeling of the SEDs I showed before, you find that this is a mildly relativistic jet, and you find that this is what the density profile looks like. R to the minus 3/2 is what you would naively expect from spherical Bondi accretion, which is sort of consistent, roughly consistent with this. There's a little bit more complexity going on here, perhaps. And this was a very highly energetic event. The total energy of the event is about 10 to the 52 ergs. And as I said on the previous slide, this event is unusual among TDEs. Most TDEs don't seem to produce jets that are similar to this. This is my taking a brief foray away from radio observations. This is the X-ray light curve of Swift J1644. And you can see at early times it's very bright and highly variable, and then starts declining with time. And at around 500 days, there is a very abrupt drop in the X-ray luminosity. So the jet, we interpret this as this is the point at which the jet shut off. And so then there's just this residual low level of X-ray emission. And what we think this is it actually connects very smoothly to the radio SEDs if you extrapolate them all the way down to the X-ray. So this is the forward shock from the outflow that has been launched and is continuing to expand into the medium. And in fact, now that we have the X-ray observations too, we can probe whether the system is really an energy equipartition. And we find to match the X-rays, you have to lower the total amount of energy in the magnetic field somewhat. But then when you do, you get this very nice model that continues to match all of the radio emission. So we should be able to continue to detect this in the X-ray and the radio going forward. Another interesting thing is that now the jet, as we've continued to monitor it, has actually decelerated to essentially non-relativistic velocities. So if you look at the non-relativistic transition point, that happened at roughly 700 days. So this is interesting because if the jet was initially pointed away from us, it would have been relativistically beamed away from us until it slows down to about this point. So if you're looking in your radio survey trying to blindly find these things, you should be able to detect them all the way out to a redshift of 2, but by the time you detect them, they're evolving very slowly. So in order to identify something as this kind of transient in a radio survey, you have to observe over a several-year period, and convincing yourself that it's a TDE as opposed to something else might be tricky. So really, radio surveys, it may be difficult to find these kind of events blindly, but they will be there, and if you have other multi-wavelength data to confirm it, that's going to be the way to move forward with this. And I should mention that all of these results on the late time observations of Swift J1644 are in a very nice paper led by another graduate student in Nito's group, Taraneh Efkatari, and that paper has been accepted to AppJ and is up on the archive. So if you want more information, I encourage you all to go check it out. So moving on to the second interesting event in our TDE radio sample. This is a tidal disruption event called Assassin 14Li, which was discovered by the Assassin survey, which is an optical survey designed to be an all-sky survey for supernovae, but has also found a lot of interesting other transients as well, including TDEs. It's very nearby as these things go. It's only 90 megaparsecs away, which makes it still one of the closest TDEs to have been discovered. This is what the optical spectrum of the event looks like. It's got these characteristic, it's got the hydrogen lines, but it's also got this characteristic broad helium feature. So it looks very similar to other optically detected TDEs. And another thing that made it clear this was a TDE and not some supernova is that if you fit the black body temperature of this event, it remained constant and very bright, very hot for a very long time. So this is something we see in TDEs, but not in, say, supernova as they cool off. So it's pretty clear that this event seems like a typical optical TDE with optical soft X-ray emission. But what makes this event really cool is the detailed radio data set that we got of this object. So starting about a month after it was discovered, we observed it with the VLA all the way across the centimeter radio band. And we see that the emission has clearly evolved over this 1-year period. So if you look especially at the higher frequencies, the radio flux density decreases by almost an order of magnitude. If there's X-ray astronomers in the room and you're used to studying supermassive black holes, that's going to sound like nothing to you because AGN vary that much in X-rays all the time. But AGN in the radio are much less variable. A factor of 2 increase in flux is a large flare. So this is really very interesting and very significant that there's this strong transient component of the emission. So if you subtract off this underlying component, you get this is what the SED of the transient component does over time. We had reason to believe, even when I wrote this paper, that there was some underlying other source of radio emission in the galaxy because there are archival detections of the host galaxy that are from 10, 20 years before the TDE actually occurred. So we put in this model for the quiescent component, and I'll show you in a couple slides. We actually are continuing to monitor this source, and the radio emission has plateaued. So there was, in fact, a quiescent component. It's still there after the TDE. So this is actually a pretty reasonably close model of the underlying quiescent emission. But now what we do is we fit our synchrotron model to each epoch of just the transient component of the emission, just like we did for the other event. And this is what we find. We find that the size of the emitting region is growing at a roughly constant rate with time. It has a velocity of about 12,000 to 36,000 kilometers per second. So essentially non-relativistic still, but very fast. The outflow energy as a function of time is roughly constant. The two different colors here are what you get when you make different assumptions about the outflow geometry. The red one is if you assume the outflow is perfectly spherical, and then the blue is if you assume that it's somewhat more beamed towards you, because you're just sort of measuring the surface area on the sky, so you has to have moved faster if it wasn't as widely opened to begin with. But one interesting thing we can do is, since we have this graph showing that the radius is increasing at a roughly constant rate, we can extrapolate backward and figure out roughly what time was the outflow launched in the first place. And in fact, when we do that, we get that if you continued expanding at this constant velocity all the way back to several months previously, the outflow was actually launched in August, which is several months before the discovery and first detection in the optical, but this field was behind the sun between about July and November when it was discovered. So it's actually perfectly plausible that this event could have had the accretion rate be peak around this time. So these histograms here are some independent modeling done by our collaborator James Guillochon. And he modeled the UV and optical and X-ray emission and predicted that the accretion rate should have first crossed Eddington in roughly this time and peaked around this time. So this is kind of roughly consistent with the period of super Eddington accretion. And this event was not as highly super Eddington as the jetted Swift event, but it does appear to have been mildly super Eddington at peak. I'm running out of time, so I'll just put this up quickly. This is just showing late-time radio observations by Bright et al. That were published recently. You can see that this is the declining emission we saw I showed in our first year, and then since then it's kind of plateaued off. So now we're basically seeing the underlying quiescent emission from the galaxy, which may have been associated with previous low-level AGN activity in that galaxy. And I just have a couple of plots, which is the last thing I wanted to talk about, which is starting to get into this idea of characterizing the population of TDE events from their radio observations. So this is just a plot showing energy of the outflow versus outflow velocity. And for comparison, I've shown the energetics of the population of type 1 BC supernovae and the population of gamma ray bursts, which are kind of the most extreme few percent of a distribution of stellar explosions. So like gamma ray bursts and supernovae, it appears that there's maybe a few to 10% of TDEs that produce these more energetic relativistic jets. And perhaps the bulk of the population is down here in this lower left corner of the diagram. And then this finally is just an update of the plot I showed at the very beginning, which just shows the compiled density profiles around supermassive black holes for the TDEs for which this is possible. And then for comparison, I've shown M87 scaled by the Schwarzschild radius of its much larger black hole, and also some direct measurements of the density in our own Milky Way galactic center. So one thing that's really, one thing that's really interesting is the yellow points here. These are the density profile we infer from Assassin 14 Li. The overall normalization of the density depends, again, a little bit on what you assume about the outflow geometry, but the steepness of the density profile is about r to the minus 2.5, which is steeper than Bondi accretion. There have been some simulations done of super Eddington accretion that suggest perhaps you might expect this. If there has been an ongoing outflow from a supermassive black hole under accreting super Eddington Lee prior to this. So possibly this is an indication that the supermassive black hole was more active in the past in this particular galaxy. But yeah, we'll definitely have to get more of a sample to find out if this is just an unusual host galaxy, or if many supermassive black holes show this steep density profile on kind of sub-parsec scales. And I think I'm out of time, so this slide is just to say new surveys are coming online in the optical that are going to find lots more TDEs. So I'm really very optimistic that our sample size will continue to grow in the next few years, and it's going to be a very exciting time to continue doing this kind of work. So I'll just leave up some of the progress we've made so far on the science questions I showed at the beginning, and hopefully we will have lots more to report in the next few years. Thanks.
Thanks, Kate. Let's take a quick break, go get pizza, and then we'll come back for a discussion with both our speakers. Thank you. That was great.
Thank you. I'm going to take the microphone off before I walk off with it.